Okay, so like I said, we're going to be talking about limits. There is really only one important thing you really have to really grasp in order to discuss calculus, and that's the idea of a limit. And of course, you have to be able to graph certain things and stuff like that. But we're not actually starting calculus right now. It's just some of the functions we'll be talking about in pre-calculus are hard to understand if you don't know the terminology of limits. And you find pre-calc teachers teaching kind of harebrained ways, using like harebrained methods to teach some calculus concepts in a non-calculus way. I don't want to do that because I know most of you are going to try and take calculus next year. So I really want you to get the real deal. And so we're diverging from the book, leaving the book for a minute. We're going to do a couple days of limits. We'll come back to chapter 3, 4, 3, 5, 3, 6, and it will all make a lot more sense. And you'll have all the calculus notation. You know how to write them. You know, write the limit problems down and stuff like that. So bear with me for a couple days as we leave chapter 3. Okay, so first of all, we're just going to start with a function, x squared minus 9 over x minus 3. And you'll notice that this function is not defined at x equals 3. Okay, so we're going to put that in there, not defined at x equals 3. Let's fill the blanks here. Not defined. So what exactly does that mean? Typically just means you don't get anything meaningful when you plug in 3. Okay, so let's try it. This says x squared minus 9 over x minus 3. Sorry, it's a little hard to read. If you try to find f of 3, you get 3 squared minus 9 over 3 minus 3. And that is 0 over 0. What is 0 over 0? It's kind of hard to understand, 0 over 0. If I had $0 and no friends, how many ways do I have to split my no money amongst these no friends? That is nonsense. That makes about as much sense as Herman and Sherman and Thurman were both twins. All except for Herkelmeyer, whose hair is this color. And they put him to bed early because he sleeps slow. Okay? None of that makes any sense. Not one of those sentences made any sense at all. Okay? 0 over 0 is nonsense. So we wouldn't have any actual meaningful answer here. And if you went on your graphing calculator and typed this, you get error, right? Okay, so it's actually called indeterminate. But that doesn't mean that it's not important, right? In fact, the fact that it is undefined and indeterminate is very important. So we would like to understand what it means graphically. Okay? So what I'd like to do now is just play around with our calculator for a few minutes, studying the numbers near 3. So maybe I was thinking we could use 2.9, 2.99, and maybe something even closer to 3, maybe 2.999. And we'll just use our calculator to investigate what the function is doing near 3. Okay? So let's get out our calculators, turn them on, go to y equals. You can see I have an old function in here. Clear that out. Okay, I need to type x squared minus 9 in parentheses, right? Divided by, and then x minus 3 in parentheses. Okay, and then do me a favor and put your calculator on the table set screen. So push a second table set, and let's just make sure it's on ask for independent variable. Can someone remind us what it means to be in ask mode? Yeah, Blake, what does that mean?
You can input numbers and it'll give you the y. The output.
Yeah, you're allowed to control the input. So it's going to ask you for an input. Now, watch what happens when it's on auto mode, guys. You need to know your calculators, okay? When it's on auto mode and you press table, watch, it generates and populates a full table. That's not as interesting to us. We were hoping to put in 2.9 and stuff like that. So I suggest we put it on table set ask mode, just for the independent variable. Okay? So now here's your table. It's empty, and we can put in anything we want. So I was thinking, let's do 2.9, which seems to give us 5.9. And we'll also plug in 2.99. That gives us 5.99. And let's do 2.999. And that seems to give me 5.999. So let's go back to our table and fill those in. We have 5.9 for this blank. 5.99 for this blank, and 5.999 for this blank. And I'm starting to think that maybe the closer you get to 3 for the x, the closer you get to 6 for the y. That's my gut feel. I would like to check just to be sure on that, or to feel more sure about that. Let's try numbers bigger than 3, yet close to 3. So let's pick a couple numbers that are between 3.0 and 3.1. Okay? So can someone give me a suggestion? 3.001. Yeah, that's extremely close to 3, right? And maybe 3.01. Okay, so let's go back to our calculator. If you type in these values in your table, 3.1, 3.01, and 3.001, you'll see that they come out to basically, from the bottom up here, 6.1, 6.01, 6.001. Okay, so I'm starting to notice some patterns, and mathematics is the study of patterns, is one way to think of math in a way. So I'm starting to think that maybe the y's are always just 3 larger than the x. Right? That seems to be what's going on. And maybe as x gets closer and closer to 3, y is getting closer and closer to 6, regardless of which side you come from. Okay, so I'm going to answer the question at the bottom. What value does f of x appear to approach as x approaches 3? I would say the answer to that is 6. It's hard to argue against that. Okay? Okay, now here's something interesting. It appears to me that f of x, so I'm going to write this, it seems like f of x is really just x plus 3. Right? Look at it. The y's are always 3 larger than their respective x values. But this isn't the function. The function was given. Look, the function's right here. Right? It's not x plus 3. Or is it? Look closely at x squared minus 9 over x minus 3. Doesn't this simplify?
X plus 3x minus 3 on the top.
Okay, let's factor this original problem, right? You'll notice that this factors into x plus 3x minus 3 over x minus 3. The x minus 3 actually cancels out, giving us x plus 3. No wonder the values in the table are always 3 larger than their x value. Okay, so let's talk about the graph now. Let's talk about the graph. I think we can just draw this line, y equals x plus 3. Okay? So I'm going to draw y equals x plus 3. That has a y-intercept of 3, has a slope of 1. Looks like this. But when I get over here to x equals 3, what did we say about the function at 3? What's the very first thing I said in this problem? I said it was not defined. See? So right here at x equals 3, I need to open it up and make a little hole in the graph. This is the answer. This is the graph, see? It's the line x plus 3, but it's missing one point. And that point is the point 36. The point 36 is a hole in the graph of y equals x plus 3. Okay, so here's my summary for this problem. What?
Is that a limit, a hole in the graph?
Kind of. I don't want to define limit yet, because it doesn't have to be called a hole in the graph. But what I want to write for this problem is just a couple little sentences, okay? The graph of f is just y equals x plus 3 with a hole at 3, 6. Okay, I think that's worth noting. Everything simplifies to x plus 3, algebraically. So what was the little x minus 3 all about? That punches a hole in the graph at 3. 3 comma what? 3 comma 6. Evidently the table seems to be saying that. Okay, a couple new ideas there. All right, now, what is a limit? Still not quite ready to answer it, but mathematically, you see how the graph was approaching 6 when x was getting close to 3? We can write this mathematically. LIM as x goes to 3 of f of x is 6. This is all brand new notation. I don't think anyone here has used it before. But what it means is as x gets closer to 3, y gets closer to 6. That's what it means. When x gets closer to 3, y gets closer to 6. All right, a couple more little notation deals before we move on to the next problem. When we were doing the 2.9 and the 2.99 and the 2.999, that's called doing a limit on the left. Okay? So this right here can be written as LIM x goes to 3 from the left f of x equals 6. What does this mean? This means as we plugged in numbers less than 3 but close to 3, we were approaching the y value 6. Okay? And the red numbers that you see here are called a right-hand limit. So this is LIM x goes to 3 plus of f of x equals 6. What is this little minus and plus superscript? See this little minus and plus superscript? The little minus means we were choosing numbers less than 3, and the little plus there means we were choosing numbers larger than 3. Okay? Okay, so there's like lots of new notation here, and I'm going to drill you as we go, okay? Let's look at our g of x function. Oh, by the way, this is called investigating a limit using a table, or some people call it tabular limits. Tabular limit. Tabular just means table, using a table. Okay? Not fable, that's a T. Okay, let's go to our next example, g of x. Am I ready to scroll? Can I move to the next one? Everyone got it? How many got it? Okay. What's so funny? All right. Let's talk about this function now. G of x is the square root of x minus 2 all over x minus 4. First thing I wanted to ask on this was, is g of 4 defined? In other words, can I plug in 4 and expect something meaningful? What do you guys think? No. The same thing happens that happened last time. If you plug in 4, you're going to get 2 minus 2 on top and 4 minus 4 on the bottom. That's 0 over 0, indeterminate nonsense. Use the table feature on your graphic calculator to investigate the limit. X goes to 4. See the little 4 right there? So we're going to study the numbers near 4. Get out your graphic calculator. Make sure you update your function to this one. Make sure you type it like this. Square root of x, and you're going to have to close the parentheses on that x. Minus 2, and then close the parentheses for the numerator. Divide it, and then open a parentheses for the denominator. X minus 4 for the denominator. You've got to type it properly, or it won't work at all. Okay, I'll do the same while you guys are working. I'm also going to clean out my old table here. All right. So we have square root of x, close parentheses, minus 2, close parentheses, divided by open parentheses, x minus 4. And we're not graphing, we're going to do a table again. Except I think I typed it wrong. Yes, I put square x, I meant to put square root of x. There we go. Okay, so in my table, notice I'm not studying 2.9 and so forth. I'm studying numbers near 4. So let's do the numbers less than 4 first. So let's do 3.9. You don't even have to write the results, okay? Just look on the screen. We've got 3.9. That gives us 0.25158. Let's try 3.99. That gives me 0.25016. And now let's do 3.999, and that gives me 0.25002, which is very, very close to 0.25. Okay, so I'm going to say that my left limit is 0.25. How do I write that? Let's practice our new notation. Okay, so we're going to do LIMX goes to 4 from the left of f of x is 0.25. And we don't use a squiggly equals, we use an exact equals here. It is converging upon the value 0.25. Okay, then let's get out our calculator and let's try numbers larger than 4. Okay, so let's clear this out. Let's do 4.1. Let's also do 4.01 and 4.001. I'm getting 0.24846, 0.24984, 0.24998. That's getting very close to what? 0.25. Right. So I'm going to go back here and write the limit as x approaches 4 from the right also appears to be 0.25. And once you've concluded that both of these are the same, you then can state that the limit in general near 4 is 0.25. And I don't know why I was using f of x. I was supposed to be using g of x all along, so let me fix that real quick. This is supposed to be g of x, not f of x. So this was g, sorry about that. But the point is, we can see that the behavior of the graph, the y value, is getting closer to 0.25, regardless of which side we approach x equals 4 from. Okay, let's just draw a quick sketch of this. Oh, question?
Oh, yeah. So when you are writing like 0.25, it wouldn't be like 0.2. You'd have to say 0.25, not just
Yes,
0.2.
0.25. Tomorrow, I'll show you how to know the answer without any calculator at all. Okay? That's called analytical limits. This is tabular limits today. We're using a calculator. Okay, but for right now, let's see at least if we can understand it graphically. What is it saying? It's saying that we have a kind of a complicated graph this time. So I'm not going to try to draw the whole thing. But one thing I know for sure is if you're anywhere near x equals 4, okay, the y value is about a quarter, 0.25. So whether you're coming from this side or from the right side, the graph is approaching the point 4, 1/4. Now actually at 4, 1/4, nothing is there. How do I know? Because g of 4 doesn't exist. But the limit exists. That means that the graphs kind of come into this point. And although it's an open hole, we do have sort of a semi-connected graph there, see? If you just filled in that hole, maybe just put your finger there, that fills in the entire graph, this graph would be fully continuous. Okay? It's just missing that one little spot. So what is a limit? Well, last period somebody conjectured that a limit is just the y-coordinate of a hole. Not quite sure, as we'll see on the next page. Okay, but that's not a bad guess. I think we can at least take the first part of their definition. I think we should write at the top of our paper, a limit is a y-coordinate. Okay, so let's go back to the top of our paper. We're trying to get a definition today. What is a limit? And we're going to start off our sentence by, it is the y-coordinate, and then we'll finish the sentence in a minute, okay? Yes?
Because limits, functions with limits are continuous, I mean, do they have inverses?
They can be continuous.
They
The
can?
ones we've done so far are not continuous.
Oh, okay.
But to answer your question, an inverse functions can exist with or without continuity. So that's a very good question. Okay, let's go on to the second set of problems. So what you're going to notice when you take calculus class, did you have a question?
No,
Oh, right, it's right here. Let me hand it out to the other 8 people. One thing you're going to notice about calculus class is that everything is taught in a fourfold manner. First you learn how to use tables, and then you learn how to use just graphs. Like these problems are all just graphs, okay? And then you learn how to do things without tables or graphs. That's called analytical or algebraic. Ashley. And then there's some problems that are just strictly verbal. You have to write sentences or whatever, okay? Or you have to word things the right way. That's why I'm so heavy on the verbal stuff. I'm always trying to get you guys to speak, right? You want to? Oh, I think I messed it up a bit. Okay, you should have one sheet that has graphs, one sheet that says special cases, and down, right?
There's graphs.
Need graphs.
Need graphs. Okay, here's graphs. Blake needs graphs. I need graphs. Okay. Bear with me here. And you need graphs too. You got the graphs. You actually need this one. And you need graphs. Sorry about that. Actually, whatever's left over will be yours. That's for you. That's our next page is the graphs. So you can title it page 2. I think you do this page, right? 4 sheets altogether. You're going to have to let me concentrate for a minute. Your special cases and your graphs. Okay. Who doesn't have your special cases? Is that you? I should say special cases. You have to run. Okay, it's coming. That's what I'm asking. Who else doesn't have special cases? No, I got all 3. Should be 4 sheets. 4. Okay. You have that one? I have that. Okay. Which of these 4 do you not have? What do you need? Okay, there's another sheet that says there are some cases where a function's limit doesn't exist. You don't have that one? You need that one? It only has 3 pages. Somebody only has 3. This is for Ashley? Pass it all back. Okay, so we're doing graphs now. And on my PowerPoint, I just have 1 graph per problem, but you have all 4 graphs on 1 sheet. So let's go ahead and look at this now. This one doesn't give us a function. This time we're just given the graph of a function, and we're not going to really guess what the function is. It looks like just a line, but we're going to try to understand the question just completely graphically. So the question is asking, what is the limit as x approaches 2? So let's practice saying that. This is how you pronounce it. You're supposed to say the limit as x approaches 2. So everyone say that. Ready to go. The limit as x approaches 2 of f of x. So everybody say of f of x. Of f of x. Okay? So the question is basically asking us to find x equals 2 on the graph paper. So that would be here. Find x equals 2. And then ask yourself, what does the graph approach on each side? Like what y value does the graph approach on each side? So what I like to do is kind of silly, but I like to draw a boy on this side and a girl on this side. The boy is actually headed this way, and the girl is headed towards the left like this. Okay? They're walking towards this point on a hill. Okay? And you are a third party, and you call the boy, and you say, okay, boy, where are you going? Now the boy will say, I'm going, listen, to x equals 2. And then you're going to say, no, I already knew that. What I meant was, what y coordinate are you approaching? What would the boy answer? If you ask the boy, what y coordinate are you approaching? The boy would say 3, right? Because he's approaching y equals 3. So you would write that mathematically as the boy, he's basically 2 minus. the boy is approaching, we'll assume this is function f. The boy is approaching 3, see? And then if you called the girl and asked the same question, where are you approaching? She'd say, I'm going towards 2 from the right. No, no, no. What y value are you approaching? What would the girl say? She would also say 3, right? So the limit as x approaches 2 from the right, that's the girl side, is also 3. And when these both agree like this, then you can conclude that the limit as x approaches 2 of f of x is 3. So these are really two-sided questions. You have to look at both sides. You have to make sure that the graphs are both converging into the same point. Now let's say that the boy and the girl finally arrive at their destination. Let's just say it's actually a Starbucks, okay? They're coming together to meet up at Starbucks, and they get their Starbucks and they have a cup of coffee, okay? That's one scenario. Listen, but let's say that the point was actually not even there. Let's say that they got here and they realized that the Starbucks was gone. The Starbucks had burned down or somehow disappeared, okay? Listen, the phone conversations would still be the same, right? You still would have heard from the boy that he was headed towards 3. You still would have heard from the girl that she was headed towards 3. The limit is still 3 even though the point does not exist. So although f of 3, although f of 2 is not 3, the limit is 3. So we need to understand that a limit is really a question of destination. It is not a question of location. It is what the graph is approaching, regardless of what's actually there. If it's filled, the answer is 3. If it's not filled, the answer is 3. Either way. Okay, question?
2 seems like such an arbitrary point. If you were to pick 3, would you still get the limit as like 4, I guess, on this particular graph? Like if you were to pick any other point, like the limit of f of x as x is approaching 3, would that be 4?
Yes.
So you can pick any point.
I did arbitrarily choose 2 as our destination, but, and that's something you have to watch out for. You've got to really pay attention down here to this number. So in this problem, it was asking us to approach x equals 2. That's why I drew this little line here. That's why I drew the boy on this side, the girl on this side. It was all based on x equals 2. See?
So a function has an infinite number of limits?
It can if it's continuous. So we could have talked about x equals 0, okay? But the picture would look a little different. First of all, the question would have a 0 here, see? And this would be the point of interest, x equals 0. Maybe it's a Togo's, not a Starbucks. And you would have the girl coming from, or the girl and the boy coming from both sides of 0, see? But the answer would not be 3 anymore. What would the answer be? 1, that's right. Because they're both converging onto the point y equals 1, whether or not it's even there. Okay? So this is why it's a little bit vague, is because the point doesn't actually have to exist for the limit to exist. The limit exists as a destination, not a location. Let's look at this one. See, this one is not asking about x equals 2 anymore. This is asking about what? X equals what? Negative 1. You can see it right here, see? So you're supposed to study this part of the graph over here. Now the point is filled. The graph is continuous. So that really just becomes a question of what is the y-coordinate of this point right here. That's really the question. That's really the answer. You're coming from the left. You're coming from the right. Either way, what y value are you converging towards? I need the y value of that red dot. Negative 2. Right? And on this problem, if someone asked you what is f of negative 1, you would say negative 2. Because the point's filled. But even if the point was open, like an empty hole right here, the destination of these 2 blue arrows is y equals negative 2. And the limit would exist either way. So the limit seems to exist quite often, even if the point doesn't. Let's look at the next one. Here we're coming towards x equals what? What does it say? 0. Right, so that would be right here. We're coming from the left, we're coming from the right. Even if this point isn't filled, what's the answer? 1 is correct. The y-coordinate of that point, whether filled or not filled. Good. Okay, let's go to the next one. This is some kind of a cosine wave. You know, it probably continues on like this. Okay. This time we're approaching what value of x? Pi. Okay, we're not going to let that intimidate us. We're going towards pi. That's fine. Pi is right here. This graph is nice and continuous. You can see that if you come from the left or the right, even if the graph was missing this point, the answer is what? What's the y-coordinate of that dot I just drew? 1/2. That's right. Notice it's halfway between 0 and 1. So I think we are correct to say that a limit is a y-coordinate. I think we can finish our sentence now. Okay? So let's go back to the top of your page, and we're going to finish the sentence. It is the y-coordinate that a function approaches as we approach a certain x value. Okay? So that's the rest of our sentence. I'll fill it in. You should copy it down. It's very important. It is the y-coordinate that a function approaches as x approaches a certain value. That's what a limit is. It's sort of the destination of the graph in a locale, certain locale. All right, let's go on and talk about some more complex situations. Okay? So, now we have a definition. Now, on the first set of problems, I gave you the function. On the second set of problems, I gave you the graph of the function. This time I'm going to give you a function, and I think you should graph it before you analyze the limit. Okay? Listen, nobody really likes the tabular method because you feel like you need a graphing calculator. Like nobody really likes plugging in 0.99 and stuff like that. So we're going to try to avoid that if we can. This graph isn't very hard to draw. Remember how to graph a piecewise function? So it's really two functions, right? It's y equals 2x plus 1, which looks like this. Passes through 1, has a slope of 2. And it's also the graph y equals 3, which looks like this. But everything sort of changes flavors at x equals 1, see? So remember what this means. This x less than 1 means you're not really supposed to draw the entire blue line. You're only supposed to draw the part that's to the left of 1. Okay, so I actually drew too much. I need to get rid of some of this. I need to have the blue line actually terminate at x equals 1. And the red line, I wasn't really supposed to draw that whole thing like that. I was only supposed to draw the part to the right of 1. See, it says x is greater than 1. See that? So I really should not have drawn the left side at all. This is the graph. You'll notice that the graph is actually open at 1. In other words, f of 1 does not exist. F of 1 is undefined, you could say. And this is actually g. Sorry, it's wait, is it f or g? It's f. Sorry. It should say, notice that f of 1 is not defined. Or you could write f of 1 equals und, you know. How do I know? Because there's no x equals 1 anywhere in this problem. Right? You've got x less than 1, you've got x greater than 1. 1's evidently not in the domain. Okay, so this is a nice little picture. Now let's go ahead and find the limit as x approaches 1. So this is naturally a two-sided question. You're supposed to come from the left. You can think of a little boy traveling along. Come from the right. You can think of it as a girl coming along. But you call them both, you're like, where are you headed? They're both going to say what? Y equals 3, right? So that's the answer to the question. The limit as x approaches 1 of f of x is 3. Even though the point doesn't exist. Did you really need a graph? Technically not, but it helps. It definitely helps. The alternative is to try imagine plugging in 0.9 and 0.99, and also plugging in 1.1 and 1.01, something like that. Okay, I like the graph. Let's go to this special case stuff. We probably won't finish special cases today, and there is no homework tonight, because it's a brand new concept. So you need to kind of have the full lesson to do the homework properly. But let's just cheat on this one and look at the graph. Okay? So this is the function 1 over x squared near 0. So let's go ahead and look at our graphing calculator. So let's go in here and let's put in the function 1 over x squared. And I'm not going to do a table. I'm just going to do a zoom standard. And I'm going to zoom in once. Okay, so zoom in once. This, by the way, is your next note card. The volcano graph, I call it. Okay, why is it volcano graph? Because it goes up on both sides of 0. This is the volcano. Oops, why is it not working? There it goes. I'm not writing on there very well. There it goes. Volcano graph. You should know that there's a vertical asymptote right up the middle here. Okay, and the graph seems to be climbing on each side of it. Well, it's kind of descending on the right. But let's talk about the limit near 0. So if you were to come from the left towards x equals 0, what do you notice about the y value?
Going up, approaching infinity.
Yeah, it's getting larger without boundary, right? So I guess you would write it like this, right? You would go Lim x goes to 0 from the left of f of x is infinity. That just means as you move in from the right, or towards the right, I mean, you're actually climbing forever. It's going up forever to infinity. See? And the same thing happens on the right side of this graph. As you come from the right of 0, it's, again, climbing to infinity. I can't write. There we go. So it's climbing. So we would write that as Lim x goes to 0 plus f of x equals infinity. And as a conclusion, then, we would write the limit in general near 0 is infinity. Okay, so both sides were climbing indefinitely near 0. So that's why we concluded this. Notice this is not a number, and it's not really a y-coordinate, but it's very descriptive. It tells us exactly what the function does on either side of 0. Yes?
Can you write equals infinity?
That's a great question. You cannot technically write equals infinity. Okay, because infinity is not a number, but you can write limits of something equals infinity.
Okay.
Because this means what is the destination of all y values? And the answer to that is exactly infinity. So it feels really iffy to do that, and it has been accepted by mathematicians. You are allowed to write equals infinity if it's a limit on the left. Because it's a destination, not a number in this case. Good question. Let's try one more. Just by transformations alone, you guys should know now that this means reflect over the x-axis. The 2 here means to vertical stretch. And this minus 2 means right shift 2. So here's your graph. It's the volcano graph. But it's over here. It's been flipped upside down. It's been shifted to the right. It's a little bit steeper. But can you at least tell me what the limit on the left is? The limit on the left of 2, limit on the left of 2 is negative infinity. See how it's dropping down into the abyss there? If you're coming from the right, the limit as x goes to 2 plus is what? Also negative infinity. And our grand conclusion, the limit as x approaches 2 in general of g of x is negative infinity. So you can see that the limit is basically negative infinity. All right. Now, what about this next one? H of x is equal to 2 over x plus 1 near x equals negative 1. So sorry, this is a little hard to read. Let me recopy this. Okay. The name of the function is h of x, and you might think you need a graphing calculator for this, but actually your parent function is just 1 over x. Which you should have memorized, right? So here's your parent function.
remember the 1 over x graph has two asymptotes there, a vertical and a horizontal. 1 over x looks like this, right? Passes through -1, -1, and 1, 1. This should actually look very familiar. The 2, h of x, you can think of it as 2 times 1 over x plus 1. This is a vertical stretch, and this is a left shift by 1. Right? So what ends up happening is everything shifts over to the left one after it's been vertically stretched. So it's just basically a steeper version of this, and also shifted to the left a bit. So here's your graph. This is now the point 1 negative, it's actually -2, -2, and then this point is now the point 0, 2. So what I did is I doubled the y coordinates, which makes these 2's, see? And then I subtracted 1 from each x. All right. Okay, so there's your graph, but the point is we're trying to discuss what's going on near x equals -1. So if you come from the left side of -1, you can see that the graph is descending down into the abyss. So we have the limit as x goes to -1 coming from the left of h of x, it's -infinity. Okay? And then on the right side, I'll do that part in blue. As you're coming towards x equals -1 from the right, you would conclude that the limit as x approaches -1 from the right of h of x is actually positive infinity. Notice the graph is going indefinitely upwards, right? So we've got one arrowhead going down, one arrowhead going up, and you notice we do not have an agreement here. These do not agree. So this is a case where the limit doesn't exist. So you would write the limit as x goes to -1 does not exist. Or it is very common to just simply write DNE. So how do I know the limit doesn't exist? It's because one arrow is going down, one arrow is going up. Okay. That kind of segues us into this next problem, this next case of problems, set of problems. You can see that sometimes a limit doesn't exist near a certain x value. So let's take a look at this piecewise function, and let's see an example of that. So we know that we're talking about x is less than 1. We have this line, 2x plus 1 line. So there you have it. And then this might look real cryptic to you here. Right here, this y is equal to -1/3 x minus 1 squared plus 4, x is greater than or equal to 1. Let me recopy that so you can see it. That's a -1/3 x minus 1 squared plus 4. But this is just a parabola, you might remember. It's a parabola with a vertex at 1, 4. The negative means that opens down, right? The 1/3 is a vertical stretch, and so forth. So in any case, what we're saying is that there is a vertex at 1, 4. This thing opens downwards. It's actually fairly wide looking. And we're only drawing the right-hand piece of it. So here is your line in red, and your curve in red. You don't need the left side of the parabola. You can ignore that. I'll erase it. But the point is, you can tell the limit doesn't exist. Why? Well, actually, this point is bubbled in. So you can see it's bubbled in for the parabolic piece, and it's open for the linear piece. Okay, so why does the limit not exist? Well, as you come from the left, right, so let's picture the boy coming towards x equals 1, right? He is rising towards a y value of 2. So you would actually write for blue here, blue is for the boy, is limit as x goes to 1 from the left appears to be 2. That's the destination of the boy. He's trying to arrive at this open red point. Now let's go purple for the girl. Here's the girl coming in. Okay, she's coming this way, and you can see that she's trying to arrive up here at this vertex. See? So in purple we could write the limit as x goes to 1 from the right of f of x is, and the y-coordinate of that point was actually 4, you remember. And here we have no agreement. These don't agree. So what do we write in that case? We write the limit does not exist. So D N E, the limit does not exist. Okay? So that's what happens when the graphs don't come together. Okay, before we start this problem, there is a slight error here. This should have been the greater than, and this should have been the less than or equal. Okay? That's pretty important. Make sure you correct that before we start this problem. Okay, so this one is dealing with a cosine graph and a sine inverse graph. There's a way to do this problem without graphing, but I'm not going to show it to you until I'm done with this problem, and I'm also going to have a disclaimer on it. Okay? Alright, so first thing is we're dealing with a cosine wave. You'll notice that this thing has been right shifted 1, right? And the amplitude is 3/2. So that means it's going to look like this. That's a little too steep maybe. It'll reach a maximum height of 3/2, a minimum height of negative 3/2, and it starts at 1. This 1 is an open end point because it says x is greater than 1. So this is sort of the right side of the graph. And then we have a sine inverse graph for x is less than or equal to 1. So you might need to review, what does the sine inverse graph look like? Well, there's some properties for it. It's in our note cards. You can look back. But it basically looks like this. Okay? And that was our graph for sine inverse. And if you remember, it has its endpoints at 1 comma pi over 2 and negative 1 comma negative pi over 2. Okay, this is just a graph you have to memorize. There are a lot of things in this class that you have to memorize. Alright? Okay, so how well do these two pieces fit together at x equals 1? And I'm going to go and color my cosine wave red at this time. So how well do the blue and the red fit together? Well, the truth is they don't fit. The point in red here, which is an open point, is the point 1 comma 3/2, and the blue one is the point 1 comma pi over 2. And you'll notice that this is about 1.57, but 3/2 is, of course, exactly 1.5. So these are not close enough, right? They have to be an exact fit in order for this to be continuous. Another way of saying it is, if you just look at the left side and we do a limit as x approaches 1 from the left, we get pi over 2. But the limit as x goes to 1 from the right gives me 3/2, and last I checked, those are not the same number. So basically we would say that this does not exist. Or you can say D and E, as we said earlier. So what makes it not exist is the fact that we don't have agreement. The limit does not exist. Now, there's a way you could do this problem without doing any actual graphing. Okay, so I'm going to do it now. Okay. Show you how I did that, how I would do that. Remember, this was the greater than, this is the less than or equal. Can't read that, let me try that again. This is the greater than, this is the less than or equal. Okay, what you could do is you could just take this 1 and plug it in right here, and take this 1 and plug it in right here, and you would get the following two statements. You would get 3/2 of cosine of 1 minus 1 equals, and that's just 3/2 cos 0, which is just 3/2. And then you could do the other one by doing sine inverse of 1, which is pi over 2, and then you can make the same conclusion that these two not the same. Not the same. The limit does not exist. Okay, but why is this method up here kind of pathetic? Let's label it pathetic method. It's not really that you did anything wrong. In fact, we're going to talk more about this later. You are allowed to just substitute to get a limit figured out sometimes. And it certainly worked out well for us. We got the same answers. We got 3/2 and pi over 2. We declared them not the same. We even declared that the limit does not exist. The reason that this doesn't really make that much sense is because what you've done is you've plugged 1 into a function when 1 was not really part of the domain. It says x is less than 1. It doesn't say x equals 1. See? So why are you plugging 1 into 3/2 cos x minus 1 if 1 isn't even in the domain? Okay, it's the same kind of thing I did, though, in a way, when I labeled this point. When I labeled this point 1 comma 3/2 earlier, I was labeling an open point. Like, why would you ever label an open point? We certainly are not saying that g of 1 is 3/2. Okay? So, anyway, feel free to use that if you need to, if you want to plug things in. But no matter who you are or how you do your problems, listen, no matter who you are or how you do your problems, you have to write this anyway. You must write all of this, no matter who you are or how you do your problems. You can use the pathetic method. Actually, a lot of teachers do. There's nothing that wrong about it, because in the end, you're supposed to write these statements as a conclusion, regardless of how you're doing the problem. All right, and that's the lesson.